So I wanted to make a brief video here. We're in section 413. We're talking about stereoisomers of cyclic compounds. And I think this is an area where a lot of students can get confused with what is chiral and what is not chiral. Especially because we have these cis and trans, like you can see the relationship between these two compounds here. You have this one cis on this side and you have this one trans on this side. However, there's no chirality here, right? You can see that with this set of compounds, we have 4 total isomers, configurational isomers, but with this one, we only have 2, and you have to ask yourself, well, why? Why is that the case? And it all has to do with symmetry, okay? Now, when you look at something like this, you could say, well, hey, I can draw a line of symmetry right here. That should tell you that this is achiral, right? But no, that's not necessarily the case. Yeah, you could do that if this was just a cyclopentane, but it's not. It has these 2 different things. It's, it's like if you had a fork, but, with a spoon over, a spoon over here and like another fork over here or something. Like it's two different things. If you were to fold this pentane towards itself, like fold this corner to this corner and this corner to this corner, the bromine and the methyl group they're not going to line up, right? This is an imperfect molecule, therefore it's chiral. And the other way that you can see that this is chiral is you could start with a carbon here and say, okay, let me see if this carbon is chiral. Well, is it attached to 4 different groups? Well, I have a bromine here, right? I have an undrawn hydrogen. And all right, well, what are my other ones? Okay, well, if I go this direction and I'm looking at, I have this carbon here. And all right, let me go in this direction. I have a carbon here. Okay, well, that's the same so far. Let's keep going, though. All right, well, what is this carbon attached to? Well, this carbon's attached to 2 hydrogens and a carbon. This carbon, however, is attached to a carbon here and a carbon here. So that's enough for that to be a different group than this one. So this methyl group, carbon attached to 2 carbons, would be our second priority here. And then this group over here, which really, is a CH2 when all is said and done. Hold on. This is a carbon attached to 2 hydrogens and a carbon. And this is a carbon attached to 2 carbons. Yeah, this is still 3 here. We're not looking at this methyl group as a CH3. We're looking at this carbon. That's my mistake. All right. So I'm just ranking these just so I can kind of keep my practice up. But you can see that there are 4 distinct groups that bromine is attached to, which is why this bromine is an asymmetric center. You can do the same exact thing with, if you start with this carbon, you can see it's attached to a methyl group. It's attached to a carbon that is attached to a bromine. Well, that's pretty unique. It's attached to this hydrogen here, and then it's attached to this carbon, which is then attached to this carbon and these 2 hydrogens. So that's kind of the name of the game here. And because this is a cyclic compound, you can have a cis or a trans form. So you can see this compound here. If we simply swap one substituent to now not face towards us, but face away from us, we're creating an isomer, a stereoisomer here. And you can do the same thing. You can say, well, I'm going to keep this methyl group here, but I'm going to put this bromine. I'm going to put this bromine going away from us. That would be the case if you were to turn this one around. If I were to flip this molecule on its back, this bromine would be going away. This methyl group would be going towards us, right? So remember, picking any of these up and flipping it on its back is not going to create a new isomer, a new compound. And if you build a model for these, that'll become very apparent, okay? The other thing to keep in mind is that these two are mirror images, right? If you were to rotate, I wonder if I can actually, I don't know that I can actually do that. Maybe I can. If you were to rotate these, like this is just the way that I like to look at it. And then if you don't believe me, you can rotate this one. And you can very clearly see that those are mirror images, right? That's clear as day. This would be your mirror here. Mirror images, but remember that they're non-superimposable images. So if we were to take this is actually a great way to do this, right? They're non-superimposable images. So if I try to rotate this and bring it over this one, it's not going to match up. You have a bromine going over the methyl, and you have a methyl going over the bromine. So what a great way to actually look at that. That's very cool. All right. So you can see the same thing here. You might be tempted to say, oh, well, I'm going to make a line of symmetry here. But it's really the same thing. You have these two different things. If you were to fold this in half, the bromine would go on top of the methyl. All right. That's your dead giveaway. You don't even have to look at the bromine and say, is it attached to 4 different groups? It's just, you can find a line of symmetry, and then you try to break it, which you can in this case. Here is the crux of this video. It's when we look at a compound like this, right? Now, you could say, well, Anthony, I can break the line of symmetry because I'm going to put a line of symmetry this way. And if I fold my bromine towards my methyl, those are going to be 2 different things. Anthony, this is achiral. And I'm going to say, well, no, it's not, because my counter argument would be, well, what if you draw the line of symmetry this way? And that's where things get really, really, really interesting. Because if you look at it this way and you fold this corner towards this corner, you're essentially folding this, you're splitting an atom, you're folding this bromine in half, and you're folding this methyl group in half, and you're looking at something that is achiral. Essentially, you're looking at a fork. My God, have I ever seen a fork in my lifetime? Clearly not. You're looking at a fork, and the other side is just a spoon. And this is not a chiral image, right? What we were looking at up here is like a fork, that has a spoon on this side, and you could say another fork on this side. But that is chiral. That's kind of like your hands. You could say there's a thumb over here. You could say there's a finger over here, or your pinky. But this, we are looking at a fork and a spoon. We're looking at something that you can split down the middle, and this is symmetrical. This is a line of symmetry. We have these equal ends of this square on both sides, and although our head and our foot are different, it doesn't matter. This is still symmetric. Now, the book's way of explaining this, and I'll show you it this way also. Look at this carbon, all right? Let's see if it's attached to 4 different things. We have a bromine, beautiful, all right? We have a hydrogen, awesome, okay? But now, okay, let's keep going. Well, if I look at this carbon, And I look at this carbon. Well, these are the same things, right? These are attached to 2 hydrogens, 2 hydrogens. Okay, so still the same thing. But then we arrive at the same place. We arrive here. We've kind of run into each other. So technically, if we're following around the route this way, our group is the same. And if we're following around the route this way, our group is the same. We're just arriving there in two different directions. So that's like the book's way of explaining it. I like this kind of like line of symmetry way, but you can do both. That way you can kind of test it out. Now, this molecule still has this configurational isomer. I think I'm using that term correctly, because you can make one of the wedges go away from us rather than towards us. However, there's still this line of symmetry. You know, if you have a product that looks like this, and it's a fork here, and it's a spoon here, or if you have a product that is a fork here and a spoon like that, these are still achiral images, right? It doesn't matter if this spoon part is coming towards us, this fork part is going away from us, or if they're both going in different directions, it's still achiral, all right? So hopefully that was kind of easy to kind of understand. Down here are two examples, again, where you can draw a line right through these things. We're splitting these atoms, and there's no uniqueness to this molecule. There's a head and there's a foot that are different, but we can draw a plane just like you're drawing the I think it's called the sagittal plane through the body, where you're cutting it into equal left and right.